Hello guys, this is RS and I'm going to start the series of videos on operation research, and the first topic that I'm going to make video on is how to formulate a mathematical model of a linear programming problem. So before starting the formulation, we have to remember few terminologies and few steps to formulate. So the first one is linear programming. Linear programming uses a mathematical model to describe the problem of concern. It deals with the optimization, maximization or minimization of a function of variable known as objective functions, subject to a set of linear equations and or inequalities known as constraint. The adjective linear means that all the mathematical function in this model are required to be linear function. The word programming is a synonym of planning. Thus, linear programming involves the planning of activities to obtain an optimal result, that is, a result that reaches a specific goal best along all feasible alternatives. Mathematical formulation of linear programming. So to formulate a linear programming problem into a mathematical model, we have to remember few steps. We have to go through few steps. The first one is key decision. In key decision, first step, we have to identify the decision variable of a given question. In step number 2, objective function, we have to formulate an objective function. We have to see in the question that whether it is a case of maximization or it is a case of minimization. Then in step 1, we have the decision variables that we have identified. We have to write it as a linear function of the objective function. The third step is constraints. In constraints, we have to see that in the question what restrictions or limitations are given. And step number 4, the last step, we have to add a constraint, a non-negative constraint, which shows that all our decision variables are positive, means non-negative. So the question that we are going to solve is production allocation problem. A company produces 3 different products. These products are processed on 3 different machines. The time required to manufacture 1 unit of each of the 3 products and the daily capacity of the 3 machines are given in the table. This is the table. It is required to determine the daily number of units to be manufactured for each product. The profit per unit for product 1, 2 and 3 is rupees 4, rupees 3 and rupees 6 respectively. It is assumed that all the amount produced are consumed in the market. Formulate the linear programming model that will maximize the daily profit. So as you can see that in the question we have to maximize the daily profit of a company that is producing 3 different products, and each product is processing through 3 different machines. Okay, so as you can see in the table that machine 1 is taking 2 minutes on product 1, 3 minutes on product 2 and 2 minutes on product 3. So the restriction is that machine 1 can only work for 440 minutes per day. This is the capacity of a machine 1. And machine 2 take 4 minutes on product 1 and 0 minutes on product 2, means product 2 is not processing through machine 2, and product 3 3 minutes on product 3, and the capacity of machine 2 is 470 minutes. Machine 3 can be the machine 3 is taking the product 1 is taking 2 minutes on machine 3, 5 minutes or the product 2 is taking 5 minutes on machine 3, and product 3 is not processing through machine 3, and machine 3 has the capacity of 430 minutes. So this is the limitation that we are given. So machine 1 can only work 440 minutes, equal to 440 minutes or less than 440 minutes, not more than that. And similarly machine 2 can work only 470 minutes or less than that, and machine 3 can work 430 minutes or less than that. Now what we have to maximize is the profit. So what we have to maximize is the product 1 is of rupees 4, product 2 is of rupees 3, and product 3 is of rupees 6. This is the profit that we have to maximize. So let's get started. As I told you before in the video that we have to remember the 3 steps to formulate a L.P. problem. So the first step is key decision, second is objective function, and third is constraint. Okay, so in step 1 we what is the key decision? We have to decide the number of units of each product to be produced. Okay, so let x1, x2 and x3. So what is x1? X1 is the number of units product 1 to be produced. As you can see that I have written x1 be the number of units of product 1 to be produced, and so is x2 be the number of units of product to be produced, and x3 be the number of units of product 3 to be produced. Okay, now we come to the objective function. So what our objective is to maximize the profit. So as you can see that I have written total profit is equals to profit on product 1 plus profit on product 2 plus profit on product 3. From this formula we are going to drive our objective function. Okay, so the profit on product 1, how we will determine the profit on product 1? As you can see that in the question we are given that the profit per unit for product 1 is rupees 4, and for product 1 we have suppose our decision variable as x1. So the profit on product 1 will become 4x1. Okay, for product 2 the profit per unit is given for product 2 is rupees 3, and we have supposed that our decision variable for product 2 is x2. So profit on product 2 will become what? 3x2. Same way for product 3 it is given that it's rupees 6, and we have supposed that our decision variable for product 3 is x3. So our profit on product 3 will become 6x3. Let's make the final objective function, because as I tell you that we have a case of maximization, so we will write here that maximize z is equal to, we will total profit is maximize z, profit on product 1 is 4x1 plus profit on product 2 is 3x2, and profit on product 3 is 6x3. Okay, this is our final objective function. Coming to the step 3, that is constraints. We have to see the restrictions that are given in the question. For example, you can see the table. Okay, it is written in the table that M1 is machine 1 and it can work only 440 days per minute in a day. M2 is machine 2 and it can work only 470 minutes per day, and M3 is machine 3 which can work 430 minutes per day. This is our restriction. So starting to write the constraint, we have to see that time consumed on M1. As I told you that time consumed on M1 should be less than 440, or it can be equal to 440 but not more than that. So our first constraint will be like M1 is lesser than equal to 440. So what is the time consumed by M1? Time consumed by M1 will be time consumed by product 2, product 3 and product 4, and it should be less than equal to 440. In the formula, time consumed on M1 is equal to time consumed by P1 on M1, and time consumed by product 2 on M1, and time consumed by product 3 on M1. So time consumed by product 1 on machine 1 is 2, and we have supposed that for product 1 our decision variable is x1. So time consumed by P1 on M1 will be 2x1. Okay, so the time consumed by product 2 on M1 is 3, and as I have told you that our decision variable for product 2 is x2. So it will we will write over here that 3x2. okay, and similarly the time consumed by product 3 on M1 is 2. okay, so we will write over here as 2x3, and as I have mentioned over here that it should be less than and equal to 440. So whatever we have done here for M1, we will do this similar thing for M2 as well as for M3. okay, so I have written over here time consumed on M2, and it should be less than and equal to, as you can see here, okay, that M1 is M2 is restricted for 470 minutes. So we will write over here 470. So I have written the formula over here for time consumed on M2, and what is it? It is equal to time consumed by P1 plus time consumed by P2 and time consumed by product 3. So what is the time consumed by M2? It is the time consumed by product 1, means it's 4, and product 2 means it's 0, and product 3, that's 3. So we will write it as 4x1, 0x2, or we will write nothing for product 2, and 3x3, and it should be less than or equal to 470. Okay, so I'm writing over here 4x1 plus 0x2 plus 3x3, and it should be less than and equal to 470. So we have to write the similar thing for M3, and time consumed by M3 I have written it as less than equal to 430. You can see in the table it's written that M3 is less than or equal to 430. So the time consumed by M3 is equal to time consumed by P1, time consumed by P2, and time consumed by P3, and that is time consumed by product 1 on M3 is 2, product 2 is 5, and product 3 is 0, and it should be less than or equal to 430. So I'm going to write it as 2x1 plus 5x2 plus 0x3, and it should be less than and equal to 430. So this is our constraint 1, this is our constraint 2, and this one is our constraint number 3. So in step number 4 we have that is non-negativity restriction. We have to write that our decision variables, that is x1, x2 and x3, they are greater than equal to 0. They can be greater than 0 or equal to 0, but not less than that. It means that they should not be negative. Last we have to write the final model, in which firstly we will write our objective function, then all of our constraints. Going to write the final model. Firstly I have to write the objective function. What was our objective function? Maximize z is equal to 4x1 plus 3x2 plus 6x3, subject to. Now we have to write our constraints. The first constraint was 2x1 plus 3x2 plus 2x3 is less than and equal to 440. Second constraint was 4x1 plus 0x2 plus 3x3, and it should be less than and equal to 470. Third constraint was 2x1 plus 5x2 plus 0x3, and it should be less than and equal to 430. And at last our fourth step, non-negativity restriction, that was x1, x2, x3 should be greater than equal to 0. So this is how our complete mathematical model of linear programming problem is looking like.